Hey guys, this is Pranav Hegde. Welcome to my YouTube channel. Today joining me is my friend Rishi Vignan Velpula.
Hello guys.
Yeah, so the topic of discussion today is the spinodal decomposition of the Cahn-Hilliard equation. So Rishi, do tell me about this equation.
Yeah, definitely. So let's talk about the brief introduction of Cahn-Hilliard equation. It is a mathematical model of the physics which describes the process of separation of microscopic phases of a binary mixture. It also describes the process of spinodal decomposition of a binary mixture. The mathematical equation is shown as below. Now let's talk about the physical interpretation of the equation. In Cahn-Hilliard equation, the evolution of concentration C, which basically depends on time x and y orientations, consists of two stages. The first stage, there is a fast phase separation, and on the second stage, a phase coercing occurs. It can be clearly shown in the diagram also.
So one of the ways of going about this would be using finite differencing. So in finite differencing, we can use the central difference method. So using an explicit Euler scheme with the second order central differencing method at a constant time step of 10 power minus 6 seconds for a node of 128 for a total time of 0.012 seconds, that is for a total iterations of 12,000 iterations, we can employ the equations given below to calculate the evolution of the concentration with respect to time. So which we get the results like as shown below. So what do you think about these results, Rishi?
Yeah, this looks fine, but let's dig deeper. Let's talk about the advantages and disadvantages of central difference method. Firstly, the advantages. The propriety in using this method is that it is easy to understand and to implement also. At least for simple material relations, the convergence rate is faster compared to other finite difference methods such as forward and backward differencing. Okay, now the disadvantages. The limitations are that it is somewhat more dissipative, so it leads to oscillations in the solution or divergence if the local Peclet number, which is the ratio of advatic and diffuser transport rate, is larger than 2. Also, the computational time is comparatively larger.
So what else do you propose we do?
So why not go for the spectral methods? I think it's faster, accurate, and easier. To talk, let's consider the equation itself, which is a fourth order nonlinear parabolic partial differential equation. Say we employ the spectral methods. By doing so, we reduce the calculation time because it is accelerated compared to the other method, and computation in spectral domain is faster and accurate as said. So it is better to use this method and provided that there is a suitable time integrator. So Pranav, what do you think, we using spectral methods will be better or not?
Yeah, sounds like a good idea. So one of the methods that we did was the explicit Euler scheme using spectral methods. One way of going about it is calculating the Laplacian. Calculating the Laplacian in the Fourier domain. So we all know about discrete Fourier transforms. We all know about inverse discrete Fourier transforms. Numerically, we do this using the fast Fourier transforms and the inverse fast Fourier transforms. So how we go about it? We calculate the Laplacian in the Fourier domain. We then calculate the Fourier wavelength, and solving this, we then evolve the concentration using forward Euler method. So we will get results like this. So it is much more smoother than central differencing method, and it is much faster to solve. So what do you think about this, Rishi?
Yeah, definitely this looks better, finer than the previous method. But yeah, there I think as we worked on it, there is a small problem here, which is the case of overflowing or blow up. The interesting phenomena that occurs while using the explicit Euler scheme is that blow up or overflowing. Overflowing is one of the aspects of numerical simulation where the algorithm generated variable is greater than the maximum value allowed for the type of the variable. For example, in the figure presented over here, you can clearly see that the occurrence of the blow up is a step-by-step manner, wherein the divergence is clearly visible in the motion capture. For example, for a time step of 10 power minus 6 seconds, the blow up occurred at approximately 18 to 10 power minus 6 seconds. whereas the maximum limit of the time step was found out to be 1.98 into 10 power minus 6 seconds.
Okay, so we have found about that. So what else do we do then? We use one other method known as the implicit explicit scheme. So most of the literature says that we have to use these method to get the best results. Let's find it out. So how we go about employing the semi-implicit scheme is for the linear terms we use the implicit discretization, and for the non-linear terms we use the explicit discretization. And in this method there are two ways of going about it. For the first iteration, we use the first equation as shown below. For the rest of the iterations, we use this equation as shown below. For the entire equation, the value of the concentration is evolved in the Fourier domain itself. So looking at the answers, we will get a simulation like this. Now, if we explore further, we can increase the number of nodes and then calculate. We get a solution like this. Now with this method, there was no blow up scene, there was no overflowing at 10 power minus 6 methods. A larger computation was done, for larger nodes was done, it was more accurate, it was more stable. Also, it took way less time than the explicit Euler scheme using spectral methods. So as said, let's look in the background of the code, like what's really happening here. First, we initialize the old and new values of the concentration. We then bring the randomly generated initial concentration into the Fourier domain. Then we calculated the Fourier wavelength. Now we have two functions. One function for the first iteration, the other function for the second iteration. As said, I'm returning the initial concentration and the first concentration here, and using the first concentration I'm returning the second concentration. So the value is transferred over here. Clearly in this for loop I have initiated that for the first iteration we use IMX1 for the first iteration, and then we use IMX2 for the following iterations. The transferring of the values is done so by this, and then we use return the Cn value in its space domain form as we need to plot it. So, after analyzing all these aspects, what do you think, Rishi?
Yeah, definitely. We can shed some light on the conclusions. So, firstly, conventional difference schemes without careful choice of parameters are often unstable. Explicit methods have a strong restriction to the time step. However, fully implicit schemes require that one solves a coupled system of non-linear systems. Therefore, considerable success was achieved using the second order semi-implicit scheme.
So that's all, folks. We have in this exercise or in this study, as said earlier, we have compared the finite differencing with the explicit Euler using spectral methods and the second order implicit explicit method using spectral methods. Of all the things, we both have to agree that the second order implicit explicit is the best ones for doing it, and the literature does say so.
Yes,
Yeah,
of course, I agree with you.
yeah. Yep, that's all, folks. Hope you have enjoyed. Do click the like button. And if this video does get 1,000 likes, I will show you how to develop an AI bot within 4 lines of code. See you.